Hi everyone, my name is Sara Takenaka, and I'm here with my teammates Sara Dedhia, Stefanie Pfahnl, and Nicole Zhao to share our CBE Senior Design Project on hydrometallurgical recycling of lithium-ion batteries. Lithium-ion batteries contain multiple components with compositions that vary depending on the battery type. This process focuses on the extraction of critical metals like lithium, cobalt, and nickel in the cathode material, as well as copper, aluminum, and graphite. The primary method of sourcing critical metals is like lithium is mining. This is why the battery value chain is wrought with environmental, social, and governance challenges. We've highlighted some of the most prominent that are directly related to mining here. A notable example of the dark side of obtaining these critical metals is cobalt mining in the Democratic Republic of the Congo. Likened to modern-day slave labor, mining practices in the DRC have been heavily criticized for their inhumane working conditions and devastating environmental impacts. From an economic perspective, demand for these metals is increasing. As electrification of vehicles and the transition to renewables continues, the demand for critical metals is projected to increase exponentially. The currently announced mining projects for lithium will not be able to meet projected supply requirements by 2030, with similar trends for other metals. On the other hand, the supply of spent battery waste will only increase. This is a large and growing untapped resource for the critical metals needed to meet energy transition needs. There's also a national security and domestic battery supply chain component to consider. China is dominant in both the mining and refining of critical battery metals like lithium, as well as a dominant player in the current battery recycling market. China has already used exports of cathode technology and other rare earth minerals as leverage against the United States in recent months amidst current trade tensions. Thus, there is a clear opportunity and need to create a domestic circular battery economy via recycling. Our process uses acid leaching of the metals via hydrometallurgical processes because it is more scalable than direct recycling and less energy intensive than smelting-based pyrometallurgical processes. Our process starts with black mass or shredded battery material, which is available on the market from other battery waste facilities. There are no industry standards for black mass, but from literature, the composition on the far right was used as the basis of our project. The goal was to develop a cost-effective and scalable hydrometallurgical process to recover critical metals from black mass at a processing capacity of 100,000 tons of black mass per year, which Nicole is going to walk you through next.
Here's the block flow diagram of our proposed process, which is divided up into distinct stages where we extract out our valuable products. The first stage is the solids removal stage, where we extract out iron, copper, and aluminum, followed by an acid leaching step that solubilizes the remaining stream and turns our critical metals into their ionic form. The remaining insoluble material coming out of acid leaching is extracted out into this next step, where graphite, silicates, and remaining copper and aluminum are removed. Finally, critical metals are precipitated out in this final stage where we extract our carbonates of nickel, manganese, cobalt, and lithium. The first step is the solid removal step, or magnetic separation is utilized to, one, collect lithium iron phosphate, which is a battery cathode material with iron oxides, and two, an adhering step that collects copper, aluminum, and aluminum oxide. The acid leaching step utilizes 2 molar sulfuric acid and hydrogen peroxide to solubilize a solid stream. A parallel configuration is utilized here to handle the large throughput of our process, along with the acid dilution step that takes 98% sulfuric acid down to 2 molar or 17% sulfuric acid. We design a unique agitation scheme with a pump around configuration to handle our mixing needs in this process. And because of the very acidic needs, glass lining is utilized for corrosion resistance. An important part of acid leaching is modeling all of the heat that is released during this process, and we have to summarize the key reactions during the step on the right. Enthalpy for each step is derived from literature and NIST databases, and acid dilution also generates a lot of heat. And because of this, heat exchangers are needed to handle the amount of heat generating following acid dilution and during the mixing pump around configuration. The next step is the current decantation step to remove insolubles. This utilizes a multi-stage process along with flocculant to remove silicates, iron oxides, and copper. And polypropylene lining is also utilized for acid corrosion resistance. Next is the froth flotation step to float out the graphite from our metal-rich stream and this utilizes a frother to help facilitate this process. Next, I'm going to hand it off to Stefanie, who's going to talk about precipitation.
So once we've reached this point, we finally have a stream that is composed only of water and metal ions, and we're able to extract out those critical metals. We do this in two pH-controlled steps, where we bring up the pH from 5 to 8, react the stream with sodium carbonate so that we create a nickel, cobalt, and manganese carbonate solid, and filter that out. That filtrate is then taken up to a pH of 12, reacted again with sodium carbonate so that we can get a lithium carbonate solid, and that is filtered out as well. The filtration process is done through multi-stage dewatering process, which includes a centrifuge, couple filter presses, a belt dryer, and a fluidized bed jet mill that gets us to a dry solid powder that is very fine and has a purity of about 95%, which is below battery standard, but above industrial standard to the point that we're able to sell it to battery manufacturers or other industrial users of lithium, nickel, manganese, or cobalt. In terms of safety considerations, material handling is a concern with black mass powder and acids. In terms of powders, they all have an explosivity hazard, and black mass itself is a carcinogen. Acids are obviously a contact hazard, so both of these materials need to have high containment. Our leaching and mixing equipment does have heat generation, so those thermal concerns are addressed through our heat exchangers and pressure safety valves. We have pretty high noise equipment that includes centrifuges and pumps, so these areas will require hearing protection, and our acids that we use will be pretty corrosive in terms of our equipment, so we do address that through polypropylene and glass linings, as well as using stainless steel or Hastelloy materials.
We'll next dive into an economics and profitability analysis. So our raw materials comprised of a few different materials where the black mass was the greatest annual cost. Our products were then mostly comprised of carbonate mix and the lithium carbonate, which were a bulk of the revenue. However, we were also able to sell graphite and the different scrap metals from the beginning of the process, kind of increasing our annual revenue size. It's important to note that metal pricing is very volatile. Just this graph of metal pricing over the last 2 years shows very high increases and decreases, going from 80% to negative 80%. And so with that, it was important to run different base case analysis to determine what we could actually price this NMC carbonate mixture at, since the price isn't really fixed, nor does it really sell on the market. Additionally, lithium carbonate does sell, and so we fixed that price at $9,758 per metric ton. This analysis also included a 60% tax credit based on the fact that Tesla recently was given a tax abatement for their Megapack factory in Waller County, Texas. So a break-even analysis showed that pricing this nickel manganese cobalt carbonate mixture at $17,980 per metric ton led to approximately a break-even with an ROI of 0% and a 7% IRR, which is pretty common for different production plants. This is, however, operating in a slight loss of $5 million. So I next wanted to see what would happen if we priced this carbonate mixture at the highest price within the last 1 year. Even a $2,000 increase led to a very sharp increase in ROI, the rate of return, and led to ultimately a profit of $125 million. So it begs the question, should we invest in hydrometallurgical separations? Because these metal demands are looking to surpass supply by 2030 in the next 5 years, it's pretty reasonable to assume increased price projections. The changing landscape could really drive profitability, and even with the case of the highest 1 year average, that opportunity to profit 125 million is only just the base. Kind of the simple laws of economics say that as demand surpasses supply, prices are just projected to increase. And so battery recycling is very critical to a closed loop supply chain. The pricing can be volatile and risky, but over time, the closer demand and supply get, the better it can be forecasted and the better demand can be forecasted across these companies and major players. Additionally, when the first EV turnover occurs on a large scale, the price of the black mass feed could decrease just because of the increase in black mass out there to be recycled. Also, integrating with large EV manufacturers like Tesla and Toyota could be beneficial because there they have incentive to reach more of a break even and to recycle their own materials rather than really aiming for these huge profit margins. We'd like to really thank our faculty advisor, Dr. Kim, as well as our professors, Professor Vrana and Dr. Holleran, and also the Department of Chemical and Biomolecular Engineering for their continual support throughout this entire process.